So we always assume 100 grams, and when we do that, we can say that we have 40.92 grams of carbon, 4.58 grams of hydrogen, and 54.5 grams of oxygen. All right, what's our next step?
Convert to moles.
You're going to convert these grams to moles. Absolutely. So we take 40.92 and we're going to multiply that by our conversion factor. 1 mole of carbon, 12.01 grams of carbon. Same for hydrogen. 1 mole of hydrogen is 1.01 grams of hydrogen. And 1 mole of oxygen, 16 grams of oxygen. Quick question for you that's not directly related here. Why are we using the grams of 1 oxygen atom and 1 hydrogen atom when we know that oxygen and hydrogen are both diatomic?
Because they're only diatomic, like when it's that single element right here, we have them in a molecule. Absolutely,
Lily. These elements now are combined in this ascorbic acid, right? They're combined in vitamin C. They're not separate and elements by themselves. And so it's not hydrogen gas, it's not oxygen gas. It's hydrogen as a part of vitamin C and hydrogen and oxygen as a part of vitamin C. All right. So 40.92 divided by 12.01. And we get 3.407 moles of carbon. 4.58 divided by 1.01. We get 4.535 moles of hydrogen. And 54.5 divided by 16. 3.406 moles of oxygen. What's our next step?
Divide all of them by the smallest mole number.
That's right. We're going to divide all these by 3.406. That gives us 1 mole for carbon and 1 mole for oxygen. For hydrogen, we end up with, we end up with 1.33 moles of hydrogen. What do we do there?
Keep multiplying it till you get a whole number.
Yeah, and what do we need to multiply by, Matthew?
4.
0.33, that's...
Multiply by 3.
We got, that's a third, so we need to multiply by 3. Yep, and so if we multiply all these by 3, I'm gonna write it up here at the top. That would be C3H4O3. C3H4O3. Matthew, to multiply by 4, what would it need to end with? Instead of 0.33?
It would need to be 0.25.
Absolutely, absolutely. So remember, 0.5 is a half, so we're going to multiply by 2. 0.33 is a third, so we're going to multiply by 3. And 0.25 is a quarter, so we're going to multiply by 4. Right? Okay, so like I said, we did that in lab yesterday. That's not too different from what we did. So let's take it one step further, sort of approaching it from a different perspective. It tells us here that this mineral chalcopyrite is a mineral for copper. And we're going to calculate how many kilograms of copper there are in 3.71 times 10 to the third kilograms of this mineral chalcopyrite. And so to do that, we need to figure out the ratio of mass for copper in chalcopyrite. There are a couple ways to solve this problem. You could find the percent copper in chalcopyrite first, and then multiply our number times that. You could multiply the initial mass of the mineral by the ratio of the masses of copper in the mineral. That would require some unit conversions. And so let's just do this first. The percent copper in this chalcopyrite, copper, iron, sulfide, is equal to the mass of just the copper. If we check our periodic table, that's 63.55 grams. And the whole thing together, we need to add copper and iron and 2 sulfurs. Who's got it? Who's got our total mass? Who's got a periodic table in front of them?
Is it 183.54?
Oops, that sounds good. 183.54 grams of copper, iron, sulfide. Right. And so that's going to give us our percent times 100%. So it gives us 34.62% copper. And now we've got our percent copper. Where do we need to go? What do we need to multiply that by? Ashlyn?
Turn it into grams.
So it asks for it in kilograms, so we can leave it in kilograms. And so we have our mass of the mineral here in kilograms. And we just need to multiply our percentage copper by that mass. And so we end up with 3.71 times 10 to the third kilograms times 34.62%. What do we have to keep in mind when we multiply by percentages?
Divide your end result by 100.
That's right. We convert it to a decimal, right? And so when we do that, we end up, oops, right? We end up with 1.28 times 10 to the third kilograms of copper. So this is another way that we can use that percent composition to help us figure out, you know, if I'm digging this mineral out of the ground and I want to know how much copper I'll get out of it, I can run a quick calculation and figure out, you know, the mass of just copper in that load of mineral. Okay. All right. One more quick example. Again, we did one kind of like this in lab yesterday. Actually, we did this exact one in lab yesterday, so let's skip it. All right, so that's percent composition and empirical formula. The way ALEKS is split, the percent composition part is on, for this week's ALEKS, and the finding empirical formula from percent composition is on next week's ALEKS. And so they are split up a little bit, but hopefully that's not too difficult to follow along. All right, so the last thing we're going to do is, the next thing we're going to do is talk about chemical reactions. Again, I keep saying that, you know, as we get further and further into chapter 3, we're really getting into the good stuff, the meat of chemistry. And so when we talk about chemical reactions, this is any process where we have multiple substances change into one or more new substances. And that's a reaction, chemical reaction. Chemists usually often use an abbreviation for reaction, RXN, reaction. So if you see RXN, just know that that's what that stands for reaction. The way that chemists most often use to get this information across about a given chemical reaction is to use the chemical equation, right? And so a chemical equation uses those symbols that we know and that we've talked about when we talk about naming and atomic symbols. So it's kind of our shorthand, right? So it uses symbols to show what happens during a chemical reaction. Another shortcut that we use for equations is EQN. And for whatever reason, a lot of people put the N as sort of a superscript when they write it. That's the way I do it. That's the way my teacher did it. And so, you know, reaction and equation, RXN and EQN respectively. When we write a chemical equation, we're always going to start with what we have to begin with. We call those the reactants. They are the ones that are reacting. And the things that we make, or the things that we produce, are called products. So it'll always be reactants on the left of the arrow and products on the right of the arrow. Right. When we think about chemical reactions, there are lots of ways to think about it. And of course, there's some wrong ways to think about it too. So when we read a chemical equation, right, we're reading this chemical reaction. We're trying to figure out exactly what's happening in this reaction. So this could mean a few things, right? We could read this as two atoms of magnesium and one, is this an atom? This O2? No, what is it?
No, it's a diatomic molecule.
That's right, it's a molecule. And so one molecule of oxygen makes two. Does anybody remember what we called ionic compounds? We had a special word for them. Yeah. We don't use it often. We call them formula units. So 2 formula units of MgO. So that's one way that we can think about this reaction, this equation. 2 atoms of magnesium react with a molecule of oxygen to form 2 formula units of magnesium oxide. Now again, generally we're not thinking about things at the atomic level. When we're doing a reaction in lab, right, we're going to do that reaction at the lab scale. And so instead of atoms, we're probably going to use moles, right? And so another way we can think about this is the 2 moles of magnesium plus 1 mole of O2 makes 2 moles of MgO. That is by far the way that we will think about it the most, talking about these mole ratios. Now notice it's exactly the same ratio as using atoms and molecules, but we think about it in terms of moles more often. There's one more way that we can think about it, and that would be to go ahead and convert these moles to grams, right? We could do it in AMU as well, but I'll just do it in grams. And so 2 moles of magnesium has a mass of 48.6 grams. So if I took 48.6 grams of magnesium, a mole of O2 weighs 32 grams of oxygen. Okay. That's going to make 80.6 grams of MgO. Perfectly legitimate way to think about it as well. We just convert those moles to grams. Right. What I don't want you to do is to think about it in terms of grams, but still use the ratio that's in the formula. Right? Don't think about this as 2 grams of Mg plus 1 gram of O2 makes 2 grams of MgO. We haven't talked a lot of physics in here yet, but one of the main laws in physics is mass conservation. I've got a total of 3 grams on the left and only 2 grams on the right. That extra gram disappeared or what? Yeah, so we don't want to do it this way, right? So don't do that, don't do that. We've got to think about these in terms of mole ratios rather than gram ratios. Even if we look at the line that talks about this reaction in terms of grams, you know, 48 to 32, that's not a 2-to-1 ratio in terms of grams. And so we need to not think about it in a gram ratio unless we have talking molar masses. All right. So using and balancing chemical equations, we need to make sure that we are manipulating the pieces of a chemical equation correctly. Right? So first we need to start with the correct formulas. Okay. We spent a good bit of time in chapter 2 talking about naming. You did well on the ALEKS part of the ALEKS that's due this week. It has naming on it, so you'll get more practice there. So we need to start with the correct formulas, right? Both for the reactants and for the products. And so if we have something like ethane reacts with oxygen to form CO2 and water, this is an example out of our book. Ethane, C2H6, we learned that from our alkane naming. Reacts with oxygen, O2, to form, that's our arrow, carbon dioxide, CO2, and water, H2O. So we need to be able to go from written out names to formulas like that and back and forth. The second rule to keep in mind when we're balancing equations is to change coefficients to balance atoms not formulas. Okay. We've just spent a long time trying to get the formulas right for the reactants, the formulas right for the products. Once we have those formulas correct, if we need to change the number of a particular atom, we don't need to go in and start messing with the formulas. We need to just say, okay, instead of 1 mole of this particular compound, we're going to have more than one. And so for this particular reaction, I've got 2 moles of carbon on the left, right? That C2 shows me there's 2 moles. I've only got 1 mole of carbon on the right. So what do I need to do?
Put a 2 in front of the carbon.
That's right. We need the 2 in front of the carbon dioxide. I've got 6 moles of hydrogen on the left in my ethane. I've only got 2 moles of hydrogen on the right in the water. So what do I need in front of the water? A 3. Once I've done that, let's count up our oxygens. I've got 2 moles of oxygen atoms on the left, and I've got 2 times 2, that's 4 oxygen here, and I've got 3 oxygen here, and 2 oxygen here. I hope you don't think that that's 40, 30, and 20. And so I've got a total of 7 on the right in the product side, only 2 on the left. And so that means that I need a 7/2 here in order to balance everything out. It's got to be 7/2 because it comes as O2 rather than oxygen atoms separately. And so we end up with 7/2. Turns out that we're not really happy with a fractional coefficient. And so we're going to remove that fraction. So step 3 here, we're going to remove fractions or eliminate fractions. Gotta spell correctly. We're going to do that by multiplying by an integer, a whole number. Right? And so we need to multiply by 2, and so we end up with 2 C2H6 plus 7 oxygen. Give me 4 CO2 and 6 waters. All right. So a couple of things to point out when we did that. Okay. Again, when we were looking at oxygens, that coefficient that's out front didn't just, this 2 here, that's not just for the carbon, that's also for whatever oxygens are in that molecule, right? It's for that whole substance. This 3 is for the hydrogen, but also for the oxygen that's in that molecule. And so those coefficients tell me that I have multiples of that whole set of elements. I have multiples of that entire compound, not just that first element in the compound. Okay. And then the last thing, of course, we can always use a double check. We just need to make sure that we have the same number of atoms of each element. on each side. We can say the same number of moles of each element on each side. 2 times 2 gives me 4 carbons on the left. 4 times 1 gives me 4 carbons on the right. 2 times 6 gives me 12 hydrogens on the left. 6 times 2 gives me 12 hydrogens on the right. 7 times 2 is 14 oxygens. I've got 4 times 2, that's 8, plus 6 times 1, that's 6. So 8 and 6 is 14. And so I'm all good and balanced here. Okay? Alex has plenty of good equation balancing practice. They do get a bit trickier from here, but not terribly so. All right, so here's one. Aluminum metal reacts with oxygen to form aluminum oxide. And so what is this equation going to look like? Catherine, what's my first element going to be?
Your first element is going to be Al.
That's right, Al. Yep, absolutely. And if Al is reacting with oxygen, Rahi, what do I need next?
O2.
O2, because oxygen is one of those diatomics. That's all my elements. Of course, I'm forming Al2O3. Take a minute to balance that completely. And then we'll get coefficients. Taylor, Michael, and May, I'm coming for you for coefficients.
Oh, Lord.
All right, Taylor, what's our coefficient for aluminum?
4.
You end up needing 4. That's absolutely right. All right, Michael, with 4 aluminums, how many oxygens?
Would it be? No, that's not it.
Okay, how about this? With 4 aluminums, how many aluminum oxides do we need?
Aluminum oxide?
Yeah.
Oh, 2.
2. So that our aluminums balance. All right. Okay, May, now that we have 2 aluminum oxides, how many oxygen molecules do we need?
3.
3, you betcha. Okay. So this is one where we ended up with 3 halves for oxygen, had to multiply through by 2. So we had no fractional coefficients. Okay. All right. So how do we use these equations, right? Once we have a chemical equation written out, how do we actually use it? Well, I'm going to write out the one that we just did. 4 aluminum plus 3 oxygen react to form 2 moles of aluminum oxide. If we look at a problem like this, what we're gonna be asked perhaps is, let's say that we know that we have 12.4 grams of aluminum, and we want to know how many grams of aluminum oxide we're going to make. Well, this is a 4-to-2 ratio. Can I just divide by 2?
No.
No, I can't divide by 2 because those are not mass ratios. Those are mole ratios. So we're going to make a box, right? This is the way that I've always thought about this. We're going to make a box. We start here with our 12.4 grams. we're going to convert those grams to moles of aluminum, right? And we're going to convert those moles to the moles of aluminum oxide. Then we're going to convert those moles back into grams of aluminum oxide. And so it's a three-step process. When we were in chapter 2 and we were talking about our dimensional analysis problems, right? We always said each arrow is a different conversion factor. And so now we're going to have 3 different conversion factors here. So we start with 12.4 grams of aluminum. Right? How do we convert from grams to moles?
Use the molar mass.
Use the molar mass. And so 1 mole of aluminum, if we look on the periodic table, 26.97, I don't remember exactly, 26.98. Grams of aluminum in a mole, right? Now here comes the new part, right? We need to convert between moles of aluminum and moles of aluminum oxide. This is what we need that balanced chemical equation for. We can't start these problems until we know what the balanced chemical equation is, because what's our ratio? Well, it's the ratio of the coefficients in the balanced chemical equation. And so we know that there's 2 moles of aluminum oxide for every 4 moles of aluminum. If you simplified that and said 1 to 2, I'm A-okay with that, right? That's the same ratio. I'm just using the ones directly from the equation. Right? And then that last conversion factor, we know how to do this. We know that 1 mole of aluminum oxide, we can calculate that in grams. 26.98 times 2 plus 16 times 3 gives me 101.96 grams of aluminum oxide. Is it clear where all of those conversion factors came from? Yeah. Okay, so now we just got to do some calculations. 12.4 divided by 26.98 times 2 divided by 4 times 101.96 gives me 23.43 grams of aluminum oxide. Remember, we're always going to carry an extra sig fig through. And so our final answer should have how many sig figs?
3.
3 sig figs. So our final answer, 23.4 grams of aluminum oxide. And so, you know, if the question had asked, how many grams of oxygen do you need to react completely with 12.4 grams of aluminum? We could have done exactly the same thing, just our box would have been smaller, right? We've gone from aluminum, grams of aluminum to moles of aluminum to moles of oxygen to grams of oxygen, right? We can use this process to move between any of the reactants or products.
Wait, so
Oh, go ahead.
Griffin, go ahead.
sorry about that. So I get how you got the 12.4 grams of aluminum, but where'd the 2 come from? The 2 grams?
Maybe this is my bad handwriting. That's a question mark.
Sorry about that.
Was there another question there somewhere?
Yeah. How do you know how many significant figures to do?
So the number that was given to us, 12.4, had just 3 sig figs. So our final number should have 3 sig figs.
Okay, I didn't know when you said that you carry an extra one over. I thought I don't know.
Yeah, so throughout the problem, you know, in our final answer, we'll make sure we have one extra. The step right before our final answer, we'll make sure we have one extra so we can round appropriately.
Okay, perfect.
And the 12.4 is a number given to us, right?
Absolutely. Okay.
How come we only solve for the aluminum moles instead of oxygen?
Because the number that was given to us was the grams of aluminum. We don't know how many grams of oxygen there were. But you're right, we have to, the assumption we make is that there's lots of oxygen in the air around us. And so oxygen didn't limit how much we could make. Yeah, this question could have absolutely been worded if you have 12.4 grams of oxygen, how many grams of aluminum oxide could you get? And it'd be a very different number. All right. This is talking about glucose breaking down in our body. So our body takes in sugar, breaks it down into water and oxygen. And that requires, water and H2O. Water is H2O. Water and carbon dioxide. And it requires oxygen, right? So we breathe in oxygen and we give out carbon dioxide. And so this sugar, C6H12O6, plus oxygen, gives us carbon dioxide plus water. Balancing it first, we've got 6 carbons on the left. We're going to give ourselves 6 CO2s, 12 hydrogens on the left. We're going to give ourselves 6 waters. On the right side now, we've got 12 oxygens from CO2 plus 6 oxygens from water. So that's 18 oxygens on the right. Now we need to subtract out these 6 here because they came from the sugar, right? And so that leaves 12. And so in order to get 12 oxygen atoms from O2, we need 6 molecules of O2. So sugar C6,
Wait.
Go ahead.
Why did you subtract the 6?
So on this side, we had 18 oxygens. I don't want to mess with the coefficient here in front of the sugar because that's going to change my carbon, that's going to change my hydrogen. And so I want to take out those 6 oxygens that the sugar had. And so 6 plus what gives me 18. Right? Turns out that it's 12. And so in order to get 12 oxygens from O2, I need 6 of them. Does that make better sense?
Oh, yeah, I gotcha.
All right. So let me erase this a little bit so we can set up our conversion box here. And so if we start with 856 grams of sugar, I want to know how much CO2, question mark, grams of CO2 are produced. We're going to follow the same path, grams to moles of C6H12O6, moles of sugar to moles of CO2 to grams CO2. So take a minute to work on that. I'll help you out. This is 180 grams per mole for the sugar. $180.2, oops. 180.2 if you want an extra 6 feet. Abigail, what's my mole to mole ratio here? How many moles of CO2 for every mole of our sugar?
1 to 6.
What goes on top?
Or, I mean 6 to 1. Sorry.
Yeah, that's how I would say it. 6 to 1 CO2 to sugar. Who's calculated the molar mass of CO2?
It is 44.01.
Okay.
How'd you get the 44.01?
That's the molar mass of CO2. So that's just 12.01 from carbon, and then 16 and 16 from the two oxygens.
Okay, perfect. Thank you.
Yeah. All right. Who has the math done out?
Is it 1,250?
Yeah, 1,250 grams of CO2. So that's a lot of sugar, right? 850 grams is 2 pounds of sugar, almost. And so if we eat 2 pounds of sugar, then we make this is about 3.5 pounds of CO2. Okay, this is called stoichiometry. Maybe that's a term you've heard thrown around, or a term you read on a syllabus or something. Stoichiometry is just a way. It's the method of moving from one part of a chemical equation into another part of a chemical equation, just using that mole to mole ratio. We'll do a whole lot more of this throughout the semester. We'll, when we talk about gases, we won't do grams anymore. We'll do liters or milliliters. When we talk about thermochemistry, we'll talk about the joules that are released instead of the grams that are produced. And so we will use this technique a lot. So make sure that you're fairly confident with it. When we come back on Monday, we'll do a few more examples and start talking about limiting reactants as well as percent yield. But that is all I have for today. I hope that you have a great weekend. Any questions before we go? All right. In that case, I will see you later.
See you. I hope you have
Thank you.
Thank you.
Thank you.
congratulations.
Good luck
Yeah.
with your